Hi class, it's me, Mr. Morris again, and we're going to do a video on photoelectron spectroscopy. This is unit 1.6 in the AP chemistry curriculum. It follows up after talking about just a review of electron configurations and orbital diagrams, and it's related to that. So I'm planning on doing most of this in class, or at least part of it in class, but I'm making this video as a follow-up so that if you miss anything, if you're absent, or if you just need to go back and review, the video is available to you. So let's get started. Photoelectron spectroscopy, or PES, is a method used to identify the placement of electrons in a single atom. So we're just talking about one atom in this case, but this helps you to identify where the electrons in the atom is, okay? So again, PES is a method used to identify the placement of electrons for a single atom. The data from PES experiments are displayed as follows. I want you to note that these are ionization energies. Okay, it's been a little while since we've talked about that. So they're ionization energies for different electrons in the same atom, and that's important to recognize. Each of these peaks is in the same atom, but it's a different ionization energy. Ionization energy is the energy required to remove an atom. So if it's hard to take an electron away from an atom, that's a high ionization energy. If it's an easy electron to take, that would be a low ionization energy. So let's go down a little bit farther and talk some more about this. In this area down here, it says that we are going to note the y-axis shows the relative number of electrons in each peak. So that's up here, the y-axis. It's the number of electrons. And sometimes it's not labeled, so you have to kind of deduce what that number is. But compared to each other, you can figure out how many electrons each has. The peak heights therefore show how many electrons would have a given ionization energy relative to another peak. So each of the peaks is a given amount of ionization energy. Recall that the closer an electron is to the nucleus, the more energy would be needed to remove that electron from the atom. So in the diagram above, the peak at 349, or we're talking about this peak right here, it's close to 347. The peak at 349 represents the electrons closest to the nucleus. Now I want you to pay attention to the scale. In this case, our 0 is over here, and the higher numbers are over here. Sometimes the scale is flipped, so you got to always pay attention to where the highest number is. Wherever that highest number is, that is the electron that is the closest to the nucleus, because it's the hardest to take away. And remember Coulomb's law, the closer you get, the closer two opposite charges get to each other, the stronger the magnitude of their attraction or repulsion. In this case, they're opposite charges, so it would be attraction. Okay? So the closest electron has the highest ionization energy, because we're talking about the energy required to take it away. In the diagram above, the peak at 349 represents the electrons closest to the nucleus. Therefore, they must be in the first shell. And we know from the electron configurations that we can have 2 electrons in the 1s sublevel. So we can come up with this idea. If that level is full, because I have another peak right here, then this other one must be full. So we can say the peak at 349 is 2 1s electrons, or 1s2. So we could write that in up here. We could say this represents 1s2. All right. And let's take a look at this Bohr atom that I have on the side. What we're saying is it is harder to take these electrons away than it is to take these electrons away. Even though it may seem kind of counterintuitive, remember, this is the highest electron energy level, but this one, even though it's the lowest electron energy level, we're talking about ionization energy, which is the energy required to remove an electron. This is the hardest to remove, so it has the highest ionization energy. And this one is the easiest to remove, so it's going to have the lowest ionization energy. And that's the idea that we want to get. The further away you get from the nucleus, the lower the ionization energy. So let's go back down here. By the way, this Bohr atom is not necessarily the same atom that we're looking at on the scale. It was just a picture from online to demonstrate how the ionization energy is compared. So the next peak at 37.1 megajoules per mole. So when we're looking at that 37.1 megajoules per mole, we're looking at the second peak. It would represent electrons in the next energy level. And of course, our next energy level would be the second shell. Note the height of that peak is the same as the height of the first peak, so we can assume that this has to represent 2 electrons. What sublevel should this be? Well, it's the second energy level. We've got 2 electrons. That would be 2s. With a configuration of 2s, well, how many electrons? We just said 2 electrons right here, so 2s2. Let's write that in up here. To S2. Continuing on. The next peak at 29.1 megajoules per mole should be the 2p electrons because that follows the 2s. Note how large the peak is compared to the prior peak. So let's go back up. We're going to compare these. At 29.1, we're looking at that peak right here and looking at the height. Again, this axis is not labeled, but it looks to me like that's about 3 times the height of the first 2 peaks. So I can pretty well assume that this 2p is 3 times as big, so it'd be 2p6. So the peak at 29.1 megajoules per mole represents 6 electrons. The peak at 3.93 megajoules per mole represents the 3s electrons, because after we go to 2p6, the next energy level is 3s. And since we got 2 electrons, we could say this is 3s2. What's that next one going to be? Well, what follows 3s2? Back down. Peak at 2.38 megajoules per mole represents the 3p electrons. Note the height of the peak is the same as the height for the 2p. The last peak would be for electrons in the 4s sublevel. So let's fill in what we've got so far. That 3p, same height as 2p6, so this is 3p6. And then this is 4s, like we just said, but notice the height of it. It looks like this is shorter than anything else, and it's about half the height of our first 2 and our 4th peaks. So it's about half the height of all of those that were 2 electrons. The relative number of electrons was 2. So the number, based on the height of this peak, the number of electrons must be 1, because it's half the height of the peaks at 3.93, 37.1, and 349 megajoules per mole. So it's half the height of 2, so this must be 4s1. And we could identify the element from that. 4s1 would be potassium. That would be K. All right. And here are a few points that we want to note when it comes to photoelectron spectroscopy. Sometimes the innermost electrons aren't shown on a diagram because the scale would be too large. These can be really long, the photoelectron spectra. We'll let you know when that's the case, but you also might see several, what it looks like, several photoelectron spectra stacked on top of each other. But if you look at the numbers, it's all one photoelectron spectrum that we just had to stack on top of itself, like 3 different layers, because if we had it all together, it would be wider than a single page. You might see a couple of those, and we'll talk about it in class if we do. The 3D electrons would typically have higher ionization energy than 4p electrons because 3D electrons are closer to the nucleus and therefore have stronger coulombic force holding them than 4p electrons. So thinking about that, your 4p electrons are an energy level higher than 3D, so they're going to be easier to take away. So typically the 3D electrons have a higher coulombic force of attraction, so they're going to have a higher ionization energy than 4p. That's what we're saying here. You can identify whether a peak represents 3D or 4p electrons by viewing the relative height of a peak and noting what the electron configuration of the atom should be. So if you know how many electrons it has, you can pretty well identify what that atom should be. So you take a turn. I want you to pause the video and then try this photoelectron spectra out and identify which element it is. All right, you might find that this is a little more challenging than you would expect. A lot of students will be thrown off because they look at these little dashes on the side and they think, oh, those must each represent an electron. That is not necessarily true. All that we know is that this is a relative number of electrons compared to each other, and we have to look at the scale. This is the highest ionization energy, so the peak that's closest to the highest ionization energy has to be the one that's closest to the nucleus. And if we've got 2 peaks next to each other that are of identical height, we can pretty well assume that those must be, and it's the first 2 peaks, we can pretty well assume this is the 1s and this is the 2s. They have the same height, 1s, 2, then 2s, 2, and what would come after 2s? That would be 2p, and since this is half the height, since this last peak is half the height of the other 2, we can assume that's 2p1. And if you were to look at a periodic table and find that element, 2p1 would be boron. Or B. Let's look at the next one. This one's a little easier. Go ahead and pause the video and check your understanding. All right, our first peak, the closest here, is 1s, and there are 2 electrons. The second peak, 2s with 2 electrons. I'm going to zoom in because I'm not writing very clearly. Okay, the next peak would be 2p, and it should be 2p6, but let's check if that makes sense. If this represents 2, then 4 would be about like right there maybe, and then 6 would be probably right about here, and it looks like that's what we've got. So 2p6. The next one would be 3s, and it's the same height, 3s2, and that makes sense. Then we would go next to 3p6. After 3p, we get to 4s. So down here we have 4s, and the last one's where you really want to check your number of electrons. It looks like it's the same height as all of the other s peaks, so that's going to be 4s2. And if you find that element, that would be calcium, or Ca. All right, this is a good breaking point for this video. I'll have some more example problems and working through the remainder of these notes in the next one so that you can just watch the part of this lesson that you missed.